Thank you for coming to our presentation, Benefiting from Bicubically Downsampled Images for Learning Real-World Image Super-Resolution. The motivation today is the problem of single image super-resolution, which is where we start from a low-resolution image and we want to reconstruct the corresponding high-resolution image. And so there have been many approaches proposed for this, but the current dominant method is to use machine learning, in particular deep neural networks. And the conventional approach is basically to generate a large data set of low-resolution, high-resolution image pairs by taking existing high-resolution images and downsampling them bicubically, and then training a large network to go from the low-resolution images to the high-resolution images. So the problem with this is that bicubic downsampling may not be such a realistic model for downsampling in real life, as this kind of modeling does not account for the camera parameters such as the noise, motion blur, the characteristics of optical lenses. And so in the kernel visualization section of this slide, you can see the estimated kernels where we're changing the focal length to generate low-resolution images and high-resolution images versus just using bicubic downsampling. And you can see that the kernels corresponding to the realistic downsampling are significantly more complex. So our idea in this paper is to basically first, given a real low-resolution image, map it to its bicubic lookalike, or map it to an image which looks like it has been downsampled bicubically, such that we can then feed that bicubically downsampled image lookalike into any generic deep learning model which has already been trained on bicubically downsampled images. And so to do this, we first train a GAN, which we call the bicubic lookalike generator, which maps the distribution of real low-resolution images to the distribution of bicubically downsampled low-resolution images. And we do this in two ways. First, we have a copying mechanism where the network is fed with identical bicubically downsampled images as both input and ground truth to prevent over-sharpening and artifacts. And second, we have our own version of bicubic perceptual loss, where the feature extractor is an SR network which was trained on bicubic downsampled images. And so an overview of our approach can be seen here. The real low-resolution image, for instance, a random smartphone image from a camera, goes through the bicubic lookalike generator, and then the output is what this image would have looked like if it was downsampled bicubically from its high-resolution counterpart. And then we use any generic SR decoder to then get the super resolved image. And so this is our proposed architecture for this bicubic lookalike generator. And for the training data, we use a dataset proposed in ICCV 2019 called the Real SR dataset, where they generated low-resolution and high-resolution images by changing the focal length of a camera, and then through some registration, they're able to generate low-resolution, high-resolution pairs. In addition, we use the div2k unknown low-resolution dataset, where they have downsampled these by unknown kernels, and then mapping them to the corresponding bicubic low-resolution dataset. So here we're comparing bicubic upsampling, an EDSR network, which is trained on real, end-to-end from real low-resolution images to the high-resolution images, DPSR, the real SR method proposed in ICCV 2019, and then our approach. So as we can see from these qualitative images, our approach produces sharper and more realistic textures. We also conducted a user study where we took images from 6 different datasets: the div2k high-resolution dataset, as there's no corresponding ground truth there, the real SR high-resolution dataset, the real SR low-resolution dataset, images from TV streams, DPED, which is a dataset of images from different smartphones, and the div2k unknown dataset, where random unknown kernels were used to create low-resolution images. So we took random images from these, and then for each competing method, and then we asked 41 participants to basically vote for which output super resolved image looked the best. And here we show a table of the percentage of votes for that particular method. In particular, blue are the votes for our method, and we can see that in all cases, the participants favored the results from our model compared to using the other methods. Thank you for coming to our presentation.